For part 3 of my tutorial, I'm just going to run everyone through Bayesian Inference and using the MCMC method in BIOMEC. For this, I'm going to run everyone through what Bayesian Inference is, what the Markov chain Monte Carlo method is, MCMC, and setting up BIOMEC Bayesian Inference inputs and analysis of BIOMEC Bayesian Inference outputs. Apologies in advance for all the maths. Bayesian inference is a very statistics heavy thing or study, and applying it and understanding what it does requires quite a bit of maths, and statistics isn't the prettiest of maths for conciseness anyway. So what Bayesian inference is you take Bayes' theorem, Bayes' rule here, which is to say that for a posterior probability where the probability of a parameter set theta given experimental data y, to calculate this, where this posterior here is of what is of interest, we require the prior distribution, so the information on the parameter set theta, like for previous knowledge, the likelihood, so the probability of the experimental data would occur given the parameter set, and also the normalization constant, so the probability of the experimental data in general. For what this is Bayes' rule, and what Bayesian inference does is it sets a likelihood function to be the likelihood of a parameter set given your experimental data y equals the probability of your experimental data given theta. And then the important thing in Bayesian inference is we are sampling the posterior distribution using the likelihood function. So we just remove the normalization function for ease and just assume that the posterior distribution of the parameter set theta given experimental data y is proportional to the prior distribution and the likelihood function. This is the general theory behind Bayesian inference. And then to identify this or sample the posterior distribution, we use Markov chain Monte Carlo method to numerically sample it over normally 25,000 samples, 40,000. You can get away with as little as 7,000, but I'll show you ways to identify that later. So what is the likelihood function? Well, the likelihood function of the likelihood of a parameter set given y is dependent on a noise model, where the most simple noise model is that of the total current difference squared, or the Bayesian total current difference squared, which is we assume that each point of your experimental data is normally distributed around the mean. So again, we go back to the mean, and we assume that there is a normal distribution of the data points like so. Something like that. And then we try and fit a function of a mean f of t, which is normally our simulation, to the experimental data, assuming the mean fit and also a standard deviation of sigma noise, where sigma noise is the normal distribution of each points in time here. Now, this can be equated in the model as a normal distribution here, but the general full equation is this one here. And an important thing with the total current difference squared is that noise is inferred as part of a calculation, whereas with a harmonic percentage, the noise is approximated from experimental data. But this is the equation for the total current difference squared. When it comes to actually calculating the variation, we generally don't use the likelihood function itself because we're only concerned with ratios of them. We generally calculate the log likelihood, or the log likelihood here. So you'll see the log likelihood a lot more in literature, where you have your total current difference squared here, and then your sigmas here and here for each point in time again. So what is this posterior distribution we're trying to calculate? Well, it normally is, well, quite simply, is just the distribution of a set of parameters as a probability. So to look at this as a one-dimensional histogram, you're generally going to get a normal, or you want to get a normal distribution of parameters with a mean parameter x theta, and then it'll have a set amount of standard deviations. This is generally what you want to get, and most of these are normalized. And when you are sampling the posterior distribution, what you're doing is you are numerically taking a point of these at a time until you build up a histogram of what the true value is, or what the posterior distribution is, using the macro-chain Monte Carlo method. This is normally in 2 dimensions, so you'll have something like theta 1, theta 2, and it will look at like something like this as a multivariant distribution like that, and it'll have a correlation and all kinds of parameter stuff. But you're sampling them in all dimensions simultaneously, where for voltammetry, your theta is generally values of E, K naught, CDL, diffusion, RU, so on. Now, what the MCMC method is it's a numerical way of sampling it. Now, the algorithm to do this is quite complex, and I recommend to do this is to read a lot of statistics books. I'll link something in the description of this video, or also the original paper, well, not the original paper, the first paper published about Bayesian inference for voltammetry has also a very good coverage of this, and if you want further information, I recommend you read that, and I'll also link that in the description. But what it is you're basically calculating a ratio of having a posterior distribution that looks like this. You sample a point, test another one, randomly generate another data point in your prior distribution, and then move to that point if it's accepted or not. And then what it'll do is it'll randomly generate another point, and if that point increases the probability of overall all 3 of the chains, it will move to it. And if it doesn't, it will stay at the original point, adding that to a normal iteration. So you'll end up having, if it's accepted, you'll have 0.1, 0.2, 0.3 in the chain, and if it's not accepted, you'll end up having 0.1, 0.2, and 0.2. And then this will just go on and on and on, and rejecting if it's not likely. And when it's accepting or rejecting it, it's calculating this ratio of the candidature point, the log likelihood of a candidature point, or staying in the original spot of the overall chain. And then it just compares it to a random uniform number between 0 and 1. And if this ratio is below the randomly generated number, it moves. More information can be shown somewhere else, but this is the general understanding of what we use. There are different ways of having different MCMC methods are available, and also different samplers that can be used. Metropolis Hastings is a common one. There's also the Gibbs sampler. We use the adaptive covariance matrix, Markov chain Monte Carlo method. So that's what we use, and it basically just varies the posterior distribution that we're sampling from to keep the acceptance rate around. We want an acceptance rate around 0.234. which is 23.4%. And ultimately what you'll end up getting is you get a normal distribution seen here, which is actual data of a normal distribution like that in a histogram form, because we've just numerically sampled it. Again, this takes thousands and thousands of simulations. So if your simulation takes 20 seconds, it's going to take a long time. So one thing we have to do is we have to figure out ways to, one, figure out whether or not we're identifying a good distribution. And secondly, we want to find ways that we can figure out whether or not we have a good convergence to an actual solution. So a way of doing that is to run multiple chains. So given a posterior distribution like that, in multiple parameters, 1, parameter 2, we will sample it and build multiple chains, say of 4. 4 is a pretty common one. We'll build 4 chains like that. And then what happens is you'll end up getting a histogram that looks something like, ideally will look something like that for each parameter, where they all look quite similar for the histograms. So mind my horrible drawing, but they'll look something like that. Ideally, they'll all look the same. It doesn't always happen like that, and a good way to identify that numerically, if they do all look similar, is the Galvin-Reumann statistic, shown here, where this is basically just a way of measuring whether or not something is converged. And generally, for something to be considered converged, for a specific parameter, it needs to have a Galvin-Reumann statistic less than 1.025. But ideally, you'll want something around 0.1. And what it basically does is it calculates approximate variance of all the different posterior distributions for each chain, and then divides it by the width function of it, or something similar, of W. These are generally functions in of themselves, so don't take this for too much credit, but that's in essence what it does, is it checks for variation between all of the different chains. And say we were to get one over here like so, that would cause the Galvin-Reumann statistic to bump up to like 1.04 or something, and you'll know that you haven't had good convergence and that you might need to you will need to redo the experiment. And also, if you end up doing 10,000 simulations and your Galvin-Reumann statistic gets to a good level in, say, 5,000 simulations, you are wasting computer time by just running too many simulations, so you can cut that down quite a bit and improve performance. These MCMC calculations on a good computer can take 4 hours. For an intense simulation, you can take anywhere from 4 days to a week. 4 hours is for an easier system. So in essence, you want to figure out as many ways as possible to get that time down and still get a good result in the end. So I'm going to just load up my Ubuntu system and show you how to set up inputs for BIOMEC calculating Bayesian inference, and just run you all through that, okay? Okay, so to do Bayesian inference, you do the exact same thing as the CMA-ES optimization. Here I have an input file for Bayesian inference. If I just click on that, you just change the words that were CMA-ES to adaptive MECSim, which stands for the algorithm we use, which is the adaptive macro-chain Monte Carlo method. The initial couple of lines of the input file are the exact same, all of these. Even I think these are the same. The number of cores to be used are just the number of threads. They need to be the same as the number of chains to run for this algorithm. The MC initial price sampling per variable, that's because of the adaptive, initially it does a bunch of prior sampling, which is just 250 times each variable for each chain, and then it will do 40,000 total samplings for the overall chain. It will then throw away 25% of a burn-in period of the total chain length, and just it'll throw that away and then report the means and covariances of the posterior distribution at which. Again, this is just the number of chains that are on. So the total number of chains is split into 4. This is just to parallelize it so you can get a larger distribution sampling quicker, because this isn't the most optimizable. And that's about it. The main thing is this needs to be either Bayes experimental harmonic percentage fit or TCDS. For TCDS, one of these variables needs to have a value 13, I do believe, which just stands for the noise that you're sampling as well, because you sample noise as part of that. Otherwise, you can also put in this parameter here as a noise function if you want to set it. And this is just the number of comparison points. So you cut, again, it's just the same. So you just cut this down. This is 2 to the power of n data comparison points. So this will just take maybe 2,000 for each harmonic or total current when doing the comparison. Again, just to speed things up. To run it, it's the exact same. We just open a terminal. We type in BIOMEC.SIMG, and then we type in BI, type in the name of the input file, which we have called sample.exptxt. And now we just run that, and it's running, and output file has been called Bayesian Inference sample exp output. Again, well, not again, but if you were to run this file, say 2 times, what will happen is it'll just call it the same file name, but it'll call it version 2 or V1, V2, so on. Here, initial setup successful, starting ADMCMC using Bayesian experimental harmonic percentage fit objective function. And this will just, here we go, just run through like this. This will take a lot longer to run. And I'll come back to it once it's finished. Okay, so I've just grabbed some old data, which is going to have a bug in it, but we'll see that. Here, it's got the exact same naming format as CMA-ES, where you're just going to have the file, input file name, the date, and then what version it is, whether or not there's another file, like, if there's a file of the same name that it's trying to make, it'll just rename a new file but call it version 1, version 2, so on. So this is obviously version 1. We click on it and it shows convergence plots, harmonic plots, probability plots, iteration log, and a bunch of other stuff which is important. Just running through the things that are different to CMA-ES. And for reference, this is just some trash data I had lying around. Here's the convergence plots for diffusion. Here, the x-axis should be the y, and there should be iterations on the x-axis. But you can see that it's working reasonably well for these. It's as incorrectly as each color represents a different chain of the MCMC, and as you can see here, one of the chains is converged on a different parameter, with this converging on a slightly different value of alpha. This is a very fast system, so it's reasonably fair for that to happen, but it's converged to a different value, which is non-ideal. So we might have to, if we were to do this again, which we have, we would go about pinning a few other parameters to try and make it all converge to a more sensible solution. Well, electron transfer rates all converged. Form potentials done the same thing, mainly because the alpha is different, so the activity is different, and by the nest equation, you're going to see a slight variation of the formal potential value. So that's that. Other things of a probability prompt. This is a posterior distribution that you try and identify via Bayesian inference. You have your histogram values. So your histograms of that, resistance, formal potential. The number corresponds to which value on the list that you're putting it in. You also have your electron transfer rates, your alpha. Here you can see what's happened with converged to a different solution, capacity scalars, and so on. Here you have your kernel density plots, which is just plotting the interactions between two parameters. Here it's resistance and diffusion. Let's say something like here you've got formal potential and diffusion. The information in the top left is the standard deviation for the x and y variables, and also the correlation between them, where one corresponds to a very strong positive correlation and a negative value corresponds to a inverse correlation, where the values can be between -1 and 1. So here's a slight positive correlation. Here's a very strong negative correlation between electron transfer rate and diffusion. That's for all the variables. Next, we just have our iteration logs, which is the full chain of all the iterations, like all the multiple chains are summed together and displayed here. Then you'll have your master input file, which is the best fit for the mean value, your Bayesian harmonics. Also with the probability plots, the histograms, the black line is the middle value and the red lines are plus or minus 2 standard deviations. So if we go back to here, you have your parallel log, which is the same thing as the iteration, but each chain is separated by a line here. So that's one chain value, that's the other chain value for like each iteration, so it's all separate. You can also have your MECSim output best fit, which is the same thing as the previous. Then you have your results file, which is just, the important thing is the date, the completion time, the number of function iterations. Here we used a very small number, 25,000. The acceptance rate, this is again a low acceptance rate. With the adaptive macro chain Monte Carlo method is trying to set the acceptance rate as 0.234. Here you can see it's a bit lower than that. That's probably a indicator that something's wrong. The next one are these values, which are what you report, which is your mean and standard deviation of the values. Then you have the comparison between input mean and MCMC mean. This is how much the mean value has varied with respect to what we put in from the CMA-ES optimization stage. And then the rest is just the covariance standard matrix value, your covariance matrix, which is just the relationship, the covariance matrix that you end up getting via the adaptive covariance, or just all the posteriors summed together. And you have your correlation matrix, which shows you the correlation between all the points here, 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 and so on. The other thing is the Gell-Rubin statistic, or R hat. Here, this is the value where you want to get your parameters under 1.025, I believe, but again, the lower the better. Here you can see that the first two parameters have converged, have a acceptable Gell-Rubin statistic, but this one and this one don't. This corresponds to alpha and this corresponds to formal potential. This is just a numerical way of showing that your multiple chains have converged to identical or very similar posterior distributions. If these are not right, your calculation is wrong and you need to redo them, and then just pin something or change a bunch of parameters, until you get something that are all acceptable. And then that leads on to the next final file, which is the R hat, which is just telling us at what iteration number, including burn-in, is an acceptable R hat has been calculated. So here we can identify if we're running the chain too long, or if we need to add significantly more. So here you can see that, for example, we see that for variable 2, it identifies to a pretty decent parameter. This pretty decent R hat value at about 3,125 simulations. So including burn-in, that would lead it to be about 4,000. So that means all the chains can be decreased quite substantially. Probably about, I'd say, or half if all the parameters acted like the second one. And the same with the fourth one here, and so on, this one here. It's just an idea that if you're running this simulation for too long, you're going to get a lot of wasteful computation time, so you can just cut them all off and shorten your overall chain. It's all ways to validate that the posterior you're getting is a valid one and makes sense, which is very important for these kind of calculations. So yeah, that's the outputs for the Bayesian inference. Thanks for listening to this part. If you have any, hopefully not much of this will change as we go on, but it probably will. In the next part, we will cover getting CMA-ES and Bayesian inference to interact with each other and work well for optimization, issues that might arise, and general tips I can give from my use of these in the previous time. Cool, thank you.